Good afternoon to all. Myself, Dr. Jin Sponsoriak. I am working as assistant professor in Marine College, Kutikanam Autonomous. Here, I would like to say something the fundamentals about the nanoscience and nanotechnology. It is included in the module 1 of the course Integrated MSc Physics with the subject title IPH 2251B Nanoscience and Nanotechnology. And now we are going to discuss the synthesis of zero-dimensional nanostructures or nanoparticles. That means here only we discuss about the synthesis of zero-dimensional. That means quantum dots. So basically, materials are classified into three types: three-dimensional material, two-dimensional material, one-dimensional material, and zero-dimensional material. In the case of a three-dimensional material, the all dimension, that means it's a length, breadth, or height, or based upon the Cartesian coordinates, all the coordinates or the size of the particle in x, y, and z coordinates are in bulk range. That means that is greater than 200 nanometer. That means x, y, z all are greater than 200 nanometer. So in two-dimensional material, two dimension are in bulk, one dimension is in nanometer. So consider a carbon coated nanoplates, or let's consider a thin film. Then length and breadth both are in micrometer range or greater than 200 nanometer, but the thickness is in nanometer. So one dimension is in nano, two dimension is in bulk, then we can say it as it is a two-dimensional material. And now we are going to consider the one-dimensional material. One dimension is in bulk, other two dimension is in nanoscale. Example, carbon nano 2, metal nano rods, or polymetric nanofiber, self-assembled nanostructures, or nano wires. In case this one dimension is in bulk, or that we can see by using our own eyes, or that is in micrometer or greater than 200 nanometer range, and it's a breadth or depth, both the other two dimension are in nanometer, and that type of material are described as one dimensional material or simply one dimensional nanomaterial. And in the case of zero dimensional nanomaterial, we can considering the quantum dots, or in the case of graphene, it is fullerene, or considering the gold nanoparticle. All dimension are in nanoscale. No dimension or zero dimension is in bulk. That is called a zero dimensional material. So first we consider the dimension is in bulk. In three-dimensional nanomaterial, all three dimension is bulk. In two-dimensional nanomaterial, two dimension is in bulk. In one-dimensional nanomaterial, one dimension is bulk. In zero-dimensional nanomaterial, zero dimension is in bulk. Reversely or vice versa, we can say that in three-dimensional nanomaterial, zero dimension in nanoscale, two-dimensional nanomaterial, one dimension is in nanoscale, and one-dimensional nanomaterial, two-dimensional in nanoscale, and zero-dimensional nanomaterial, or dimension are in nanoscale. So the zero-dimensional nanomaterials are, which was all measured within that in nanoscale. All dimensions are measured in nanoscale. Or another words, we can say that no dimension are larger than 100 nanometer. That means all dimension, length, breadth, height, everything, all dimension are in nanometer scale. Now, based on this, the zero-dimensional nanomaterials are classified into four type: inorganic based nanomaterial, carbon-based nanomaterial, organic nanomaterial, and composite nanomaterial. So we want to discuss how we can synthesize this zero-dimensional nanostructures. The fundamental process of the synthesis of nanomaterial is the nucleation process. Nucleation process is the initial process or initial step of the formation of the crystal form from a solution or liquid or from a vapor. So we have a liquid solution, and from that we want to prepare or we want to grow a zero-dimensional material. So once there is a solid phase is started to form, and the first that initial phase or that initial process of the formation of this nanomaterial, that is called the process of nucleation. So nucleation can be defined as a small number of ions, atoms, or molecules that become arranged in a particular fashion or pattern, characteristics of that crystalline solid. With that nucleus have the all the properties of that crystalline solid, forming a site upon which additional particles are deposited as the crystal grows. So nucleus is the first formed phase, and the all other particles or atoms or molecules which are aggregated together to this nucleus, and it undergo further growth, and the crystal is formed. So the formation of the first step or the synthesis of first step of a zero-dimensional nanomaterial or nanostructure, it is defined as the nucleation process. And based upon the nucleation, the process or nucleation process is categorized into two: homogeneous or heterogeneous nucleation. Homogeneous nucleation is also called spontaneous nucleation. And in that case, there is no additional material is required or there is no foreign material is required to start the nucleation process. But in the case of a heterogeneous nucleation, we add any another particle, that we can say any foreign particle, to our solution. Let's consider the solution growth. We have the solutions of the precursors, and we add any material to that one, any foreign material or the seed of the crystal, the fundamentally very small tiny single crystal is added to that. Then all the atoms or molecules or ions are aggregated together to that nucleus or that foreign body. Then that type of nucleation by the addition of any foreign bodies, that we can say that the heterogeneous nucleation. So the homogeneous nucleation, there is a homogeneous or spontaneous nucleation, there is no any foreign particle. But in the case of heterogeneous nucleation, the nucleation speed is increased or nucleation is started by the help of an additional particle of any foreign bodies that we are added to our solution. And that type of nucleation is called heterogeneous nucleation. And based upon the thermodynamics or quantum mechanical base, we can say that the critical size, let's consider a nucleus which is started to grow, and how it's depend upon the further growing process. Let's consider here 1, 2, 3, 4. Four nucleus are started to grow. And the rate of growth of first one is very high, second one is very low, third one is very, very low, or something like that. So the first nucleus is started to grow. So let's consider this graph of the radius of the particle, or let's be consider the radius of the nucleus versus Gibbs free energy. And we can say that the Gibbs free energy is started to increase when the radius of the nucleus increases. And a particular value, the Gibbs free energy become maximum, and it started to decrease by increase in radius. And that particular radius or that radius of that nucleus is called the critical radius, that is represented by the letter R star. So Let we consider our precursor solution, and in which the solutions in which we have the atoms or molecules or ions, which started to the nucleation process by the applying of any temperature or by the application of the supersaturated solution. So the Gibbs free energy started to increase by increasing the radius of the nucleus. But a particular value, the radius, the Gibbs free energy increases and it reaches to a maximum value. And that value is called critical radius, or it is represented by the letter R star. And after that, the Gibbs free energy is decreased and R, the radius of the particle increased. That means only the nucleus which attain the critical radius will undergo the further growth. If you have 1, 2, 3, 4 nucleus, in which only 1 or 2 attain the critical radius, only that is further grow, or are the atoms or ions or molecules aggregated together to that molecule which only regains to that particular critical radius. All the other nucleus dissolve into our solution. So the dependence of Gibbs free energy G on critical radius, that is represented by this graph. We can say that there are 5 processes. First one, the process of monomers, which are aggregated together and it is grow up to the critical radius R star. Then only it is further grow. And it makes some bonds and another nucleus or another atoms or molecule aggregate together. So all these nucleus is started to grow and it further it is enlarged in its size. So below R is R star, a reversible process. That means it does not be undergo further growth. And if R greater than R star, if the radius of the nucleus is greater than the critical radius, it is an irreversible process. That means the further growth that nucleus does not regains to its original monomer form, or it further grow and form a crystal. So that we can only define in terms of Gibbs free energy, and in the terms of solution growth, we call this process is also be called Ostwald ripening process. The fundamental in modern technology for the solution synthesis of quantum dots. That means also this is the same process. The atoms or molecules or ions started to grow, and some in which only some nucleus further grow and form a crystal. All the other nucleus dissolve into the solution again, and which is joined together to the nucleus which have a particular size, or that is called the critical radius. So the Gibbs free energy in terms of free Gibbs free energy, and also in terms of Ostwald ripening, we can say the growth of a crystal or the nucleation process in terms of Gibbs free energy, or in terms of our thermodynamics curve. So up to here, it is a reversible process. And above that, it is a reversible process and the nucleation started. The nucleus is further grow and this crystal or this nucleus further grow and form into its crystal form. So these are the basic equations that we needed to express this graph. So this is the Gibbs free energy diagram with the critical radius. Let the Gibbs free energy is actually increasing to all the molecules, but only for the molecules which attain R equal to R star, and at that value, or at this R equal to R star, this free energy started to decrease. And that time, the nucleus is undergo further grow. And the value of delta G, that is the Gibbs free energy. There we have two variable here. delta G depend upon 4 pi r square. Let r is the radius of the sphere or our spherical nucleus. Then area 4 pi r square means the area into gamma. So that is the total terms of what, or total surface energy. Total surface energy into total crystal free energy. That is the Gibbs free energy. So for the Gibbs free energy, we got to add the surface free energy and the volume free energy. So 4 pi r square into unit surface free energy gamma into 4 pi 3 pi r cube into crystal free energy delta GV. And again, it can be, we can write it in terms of supersaturation of the solution. And that is equal to minus kBT logarithm ln of S divided by V, where S is the supersaturation of the solution and V is the molar volume of the solution at this particular supersaturation. And we also find out the delta G value of critical. So we can just be add this R equal to R critical value at this equation. And this equation is for the homogeneous nucleation, because the nucleation process is different in a homogeneous and a heterogeneous nucleation. By the addition of any foreign bodies, any helps to our solution to further grow, the Gibbs free energy again start to decrease and the rate of growth is increased. These all details are here. I taken it from the reference. You can choose the reference which this DOI number, and with this reference you can download the text reference, or I will send this reference journal for you. All these details explained here. And we are going to calculate the rate of nucleation with respect to time. So this is an exponential graph, this dn by dt, where a is the exponential factor and it is depend upon the delta G value of the critical, and it depend upon the Boltzmann's constant at that particular temperature. Or again, these are the all the factors in terms of the dependence of the rate of nucleation with respect to time. Dn by dt is equal to a exponential 16 pi gamma cube v square divided by 3 kb cube t cube ln of s all square. Here gamma is the surface energy and v is the molar volume of the solution. And kb is the Boltzmann's constant, T is the temperature in Kelvin, and S is the supersaturation of the solution. So these are the factors affecting. Surface energy is dependent on, temperature is dependent on, supersaturation is dependent on, or finally we can say that the Gibbs free energy is depends the further growth or the nucleation process. So here, this is the term I already says that the nucleation process that is different for homogeneous and heterogeneous nucleation. So the Gibbs free energy of the critical Gibbs free energy of the heterogeneous nucleation is equal to 5 times of the critical free energy of the homogeneous nucleation. And phi is called the factor of depends on the contact angle theta. And phi is equal to 2 plus cos theta into 1 minus cos theta whole square divided by 4. And phi can be illustrated in terms of contact angle. That means when we add a foreign body or any substrate to our solution or our precursor solution, then the wetting angle is dependent on the growth. That means it is does not wet, there is no further growth. So if we add any material, let's consider this black material is added to our solution. Then one atom or molecule is attached here. Again, it is started to attach another particle or molecule and it is aggregate together and further growth. So it depend upon the angle theta. If the angle is theta is only an acute angle or the wetting angle is acute, then it is further grow, and it is obtuse, there is no further growth is happening. And that is well explained in the following diagram. The nucleation process is depend on the function supersaturation. That means when the supersaturation is increased, dN by dt or rate of nucleation is increased. On it also depend on the temperature. When the temperature in Kelvin scale is increases, the rate of nucleation process is also increases. But the surface energy is in the reciprocal dependence. Or when the surface free energy is increases, the rate of nucleation is decreases. That means when the temperature and supersaturation of the solution increases, the rate of nucleation in atomic unit is and any arbitrary unit that is increased. But when the Gibbs free energy is increases, or here it is explained in terms of gamma, when gamma is increased, the dN by dt is decreased. It is for a particular V or volume of 3.29 into 10 raised to minus 5 meter cube volume raised to minus 1 of CDS cadmium selenide sample. It is a data obtained also from the previous reference. And these are the basic fundamentals of the nucleation process of the formation of a zero-dimensional nanomaterial. Thank you.